Now that we went back to our original motivation of calculating areas using the integral, we're going to go through a few more applications of integrals, and in this particular video we're going to talk about arc length and how we can obtain an integral formula to get the length of a piece of curve. Specifically here we're going to focus to the graph of a differentiable function, and more specifically a piece of the graph that corresponds to what lies above a closed interval AB. So something like that. We want to calculate the length of this piece of curve. We're going to approximate it with the lengths of curves that we know how to calculate. And for now it's not a lot, it's essentially line segments, and of course therefore polygonal curves that are just the sum of the lengths of line segments. So the reason why we proceed this way is because if we pick a few points on the curve and join them, then we get a polygonal curve that is, well, if we have just a few points like that, a rough approximation of the length we're looking for. But if we take more points, we get something that looks like it is closer to what we want, and we can expect that taking more and more points we would get a better and better approximation of the lengths we want to obtain. So to do that more precisely, let's start with the roughest possible approximation, just taking the line joining the two endpoints, and let's look at its length. So we're joining the point of coordinates a f of a and the points of coordinates b f of b, and we want the length of this line segment. And this is easy to obtain if you observe that here we have a right triangle and that the length we're seeking is simply the length of the hypotenuse. The horizontal side has length b minus a, and the vertical side has length f of b minus f of a, and because this is a right triangle, the length of the hypotenuse is going to be the square root of the sum of the squares of the other two sides. In other words, the square root of b minus a squared plus f of b minus f of a squared. So now, of course, we don't want to do that with just one line segment that joins the two endpoints. What we want to do is take a subdivision of the interval AB, just like that. Let's call this subdivision sigma. So the first point is A, the last point is B, and we have n plus 1 points that split the interval into n subintervals. And we want to look at the length of the corresponding polygonal curves that is going to join the corresponding points of coordinates xk, f of xk. So these are points that are on the graph corresponding to a first coordinate xk, where xk is one of the points that we use for the subdivision. The length of this polygonal curve is of course the sum of the length lk, where lk is simply the length of the line segment that joined the extremities of the kth subinterval, so the one from xk minus 1 to xk. And this length, according to what we have seen just before, we can use the same argument. We're joining 2 points on the graph. This length is going to be the square root of the square of the difference in x values plus the square of the difference in y values. So this is given by the square root of xk minus 1 squared plus f of xk minus f of xk minus 1 that we square. And of course this is just for one line segment, and we're going to add that from 1 to n, so for each one of the n subintervals, and we obtain the length of this green polygonal curve. Now we want to rewrite this expression differently, and to do that we're going to apply the mean value theorem to the function f on the interval from xk minus 1 to xk on this particular kth subinterval. And what it gives us, of course, recall that the mean value theorem simply states that if the function is continuous on a closed interval and differentiable on the open interval, then there is one value inside the open interval where the derivative takes as a value the average rate of change of the function on the interval, which is simply the difference of the values of the function at the endpoints divided by the width of the interval. We're writing this slightly differently, simply multiplying both sides by the width of the subinterval. We get that the difference f of xk minus f of xk minus 1 is equal to the value of the derivative at that particular point that exists from the mean value theorem and is between xk minus 1 and xk, multiplied by the width of the interval xk minus xk minus 1. Now we're going to call this width of the k subinterval delta xk, just for the sake of notation to get things a little easier to see. And with this notation, if we go back on the top to the formula for L of sigma, where sigma is a subdivision, we have xk minus 1 squared. This is going to be delta xk squared. And using this result that we have obtained from the mean value theorem, the second term under the square root is going to be f prime of xk star delta xk that we square. Well, this xk star again is some point between xk minus 1 and xk. Factoring delta xk squared under the square root, this is multiplied by 1 plus the square of the derivative of f at xk star. This delta xk squared, we can pull it out of the square root, and what remains under the square root is simply 1 plus the square of the derivative of f evaluated at xk star. Now you see that what we obtain is simply the Riemann sum of the function square root of 1 plus f prime of x squared for the subdivision sigma that we've been considering. So now the consideration that we have seen before show that if I get more and more points, in other words, if the parameter of the subdivision goes to 0, I'm going to get closer and closer to what I want for the actual length of the graph of the function f between x equal a and x equal b. In other words, I'm looking at the limit of these Riemann sums as a parameter. I'm taking the limit over all subdivision as the parameter of the subdivision goes to 0. And as you know from the way we have defined definite integrals, what we obtain in this process is the integral from a to b of the function for which we have Riemann sums, in that case a function square root of 1 plus f prime of x that we square, and that will give us the length of the curve y equal f of x for x between a and b, provided that f is a differentiable function, continuous on the closed interval ab, differentiable on the open interval ab. And so that gives us a nice integral formula to calculate the length of the curve that we're looking for. In practice, however, these integrals turn out to be often difficult to calculate, and there's not a lot of example we can give now. You will probably see a few more examples to illustrate how to use techniques to calculate integrals that you will see in Calc 2. But in this Calculus 1 class, this example of, or some simple variant of it, is essentially what we can calculate for the integral. Namely, we're trying to find the length of the curve y equal x to the 3/2, in this case for x between 0 and 1. So just applying the theorem, this length is going to be given by the integral from 0 to 1 of the square root of 1 plus derivative of x to the 3/2 squared. But the derivative of x to the 3/2 is 3/2 x to the 1/2. And when we square that, we obtain 9/4 x to the 1/2 that we squared. That gives us just x. So we end up with the integral from 0 to 1 of the square root of 1 plus 9/4 x. That is not hard to calculate because we can do the simple substitution 1 plus 9/4 x for u, and then du is of course 9/4 dx. What we have under the integral is not 9/4 dx, but simply dx. But dx can be written as 4/9 of du, so we're going to replace dx by 4/9 of du, and root of 1 plus 9/4 x by root of u. So we obtain 4/9 integral of root of u du. And because we're doing a substitution in a definite integral, we have to change the bounds of integration. When x is 0, u is what we obtain by plugging x equals 0 in the formula for u. So in that case, u is 1. And when x is 1, we plug x equals 1 in the formula for u, we get 1 plus 9/4, and that's 13/4. So we obtain the 4/9 of the integral from 1 to 13/4 of root u du. To calculate this integral, we can use the fundamental theorem of calculus. It's easy because it's easy to obtain an antiderivative because root of u is simply u to the 1/2, so we can use the power rule. We get u to the 3/2 divided by 3/2, which we can write 2/3 u to the 3/2. So I have 4/9 multiplied by 2/3, and then the function u to the 3/2 that I'm going to evaluate between 13/4 and 1. So the 4/9 of 2/3 gives us 8/27, and this is multiplied by 13/4 to the 3/2 minus 1 to the 3/2, which is 1. Now in the next video, we're going to look at other applications of integrals.